After recording the last video, I realized the audio was a bit crappy, but generally speaking, um, we covered most of what matrices are all about. Matrices are all about. So we have different kinds of matrices, and one important functionality matrices provide us with is what we call the inverse. So when we inverse a function, it enables us to do multiple things like solving unknowns, solving systems, and doing some great magic. And the inverse can be retrieved through, if it's a 2 by 2, then it's the determinant flipping the signs and flipping the location of different diagonals. Um, we've also seen the identity matrix. The identity matrix is like the one in multiplication, so it really has no so it doesn't really change the form of the matrix. And yeah, and it's very important for us to know that multiplying any matrix by its inverse should yield the identity matrix. There are multiple ways to get the determinant through. Um, there are multiple ways to take the determinant of the matrix in more than 2 by 2 matrices, and one way is to do the minor cofactor the educate approach. So you basically start with one, and then you'll be left with the other remaining, and then you'll get the done. Then you add and do the subtraction. It's something we've seen is right here. Yep, this is the determinant of the function, but not the inverse. You can also use the identity matrix um, to get the inverse. This is called Laplace expansion, just so you know. Laplace expansion. So if you multiply, uh, so if you want to solve for x, multiplying a by the inverse would yield x equals b multiplied by a inverse. If it was the other way around, then a inverse multiplied by b, and commutative property can't be sufficed here. So it's very important to preserve the orders as they are before we start. Yeah, this is an important example where you decide on those, and it's also very important to know that you shouldn't be so if you started off with bus and train in this case and the unknowns on the left hand side, then it's in this form, otherwise it's transposed to this form. But why you should do this is very important, because there's a note here. Important to check how this all works in the train and bus example here, especially on how to choose the rows and columns. The example on the child and adult are both multiplied and added to the same category. Example, child multiplied by bus, adult multiplied by bus. So this one is to suffice that child and adult, you would multiply child by bus, then child by bus in the second row, and so you would multiply by bus and train for both the child and the adults. Okay, some inverses do not exist, and this is very important to know. And this is can easily be determined and detected if the determinant is actually zero. This is usually called a singular function. There's also another approach um, to find. This is where we stopped in the last video. There's another approach to find the inverse of a function using the Gauss elimination. Um, okay. Um, okay, we can use another approach to get the inverse function if it's not a 2 by 2. We can use what is called minor cofactor and educate. Multiply that by 1 over the determinant. Here's how it works. Not as straightforward, but it requires a lot of steps. It's good to know it exists, but I don't think it's a good practice since you can achieve the same using row elimination. Let me just go through that, swift through it, and just ignore it. Like calculate the matrix of minus, then turn factors, educate, and so on. Determinant. So this is the way we calculate the determinant daily. So if you take an element just like how we see in this J, and then change the signs, and then transpose, and you will multiply by the determinant. Now you can just sort through it. If we ever need it, we will know that it exists, and we can revisit it again if ever need be. Now the matrix to use when solving systems is called the augmented matrix. Now if we have a system that needs to be solved, like what we used to do earlier is that we take two functions, use elimination and no substitution, and then we get a new function. We would also use the third function along with it, and then solve the system accordingly. You'll have two functions or two equations, and then you would solve it accordingly. We have both substitution and elimination. Now, now these rows in the matrix are coefficients of the equations, and for any missing variable, you get a zero, just like that. What else is really important here? Now it looks like we have a 2 by 2 matrix. We have two matrices. But now this. Why does x and y go there? Because when we multiply matrices, the left side becomes yeah, which is the original left side of our equation above. You might like to check that. So this is what you would want to produce. Now we can use what we have used earlier, having ax equals b, multiplying the inverse by b would get the results. First, so solving two systems, first we need to, like ax equals b, first we need to solve, get the inverse. Now, yeah, so the inverse is the left hand side, so on the left hand side multiplied by this side. 6 minus 4, 27. Yep, which is this multiplied by 6 minus 4, 27. Just this one, and this is what you would get. Now above that we have the x after the a, yes, x after the a, but if it was the other way around, and here the solution should change to suffice the above. Keep in mind that if x is first, it has to be transposed to suffice the matrix rule of the number of columns should match the number of rows of multiplier. Number of columns should match the number of rows. Number of columns should match the number of rows. Now this is not a solid rule because here we actually have two columns, two rows. So for a 2 by 2 it really doesn't suffice. multiply this by the inverse of this, and that's where we get similar results. We can also solve the above using, there's another way to solve this, not using the inverse, but using the row elimination operations. So elementary row operations, we would get three main operations that we could use: swap, scale, and pivot. The swap is when we swap two rows, like bring this one here, like R1 with the R3, for example. It's important to keep track of all operations carried out to know how the solution was derived. When you swap rows, you use the following notations. Okay, swapping does not change the solution, just the form. Just like in deciding which order of equations to eliminate first, this also means that it does not change the plane. Oh, okay. So you get the swapping, you need to set these forms, and then you can do the scaling, which you multiply by scalar. But you have to indicate it where they, so you replace, so what you're doing is, like, replacing is supposed to be replacing by its original step. In this case, you're actually replacing the original. So you do whatever it takes, and then you do the pivot, in which you flip some addition, multiplication, whatever it is, and then you replace it by a certain row. Whatever it is that you're trying to achieve now, but you do different kinds of operations on them. Pivoting however changes the plane. Pivoting changes the plane, anything else does not. Since you're getting a new function, recalling the slope notes that when eliminating the variable, assuming the graph is parallel to the variable. In this case, when a coefficient changes to 0, the plane would be parallel to that corresponding variable. You see the graph below, note how the second function plane is graphed. It's actually parallel. Okay? So it should move to be parallel to the x-axis. We've obtained the 0 of the second root and parallel to the x-axis rotating around the point of intersection. We keep pivoting the plane while we obtain the 0 to keep changing parallel to or 0 appeared. For example, the last function when we try to obtain 0 for both the first and second column, we get a place parallel to x and y. Rotating around the axis, it would look like this. Okay. The idea of the operation swap, scale, and pivot is to perform Gauss elimination. Utilize the above methods to reach a solution for the system. As in the example above, we eliminated the x from row 1 just to reach the row echelon for. So in Gauss elimination, the gauge just specifies zeros and ones. Echelon form requirements. Each leading entry must be 1. Each leading entry to the right of the leading entry pivot. Assuming the row echelon form, change the matrix back to equations form and solve for the variable we need from there using substitution. However, there's also another approach called Gauss elimination, which we keep working with the matrix without doing the substitution. Gauss elimination is just echelon form, where you have the main diagonal and the rest are zeros. Its leading entry is right most of the leading entry above it. Rows containing all zeros are last. Its leading entry must be a non-zero entry. So there is just echelon form. Okay, but we do that in a separate video.